Hello, everyone. My name is Jeanine. I'm a senior data engineer at Mirakl. And today I'll be talking about how to extract the unexploited wealth of data found in product images in order to leverage it to further enrich seller catalogs. How? Using vision language models. And what this talk will be about is mostly about how to make it work at scale, in production, and within budget. But first, a quick word about Mirakl. Mirakl is the world leader of SaaS marketplace solutions. It caters to 450 customers worldwide, helping them increase their revenue. And today we're at the forefront of agentic commerce with two of our new products, Mirakl Nexus and Mirakl Catalog, both leveraging GenAI and helping operators and sellers reach their full potential. Last year at Mirakl, we released a new feature called the Catalog Transformer. The Catalog Transformer allows any seller that want to sell their products on marketplaces to transform their data from custom format to operator-ready data. How? Definitely using GenAI by doing transformations, enrichments, translations. And the best part about this is that what used to take 15 days of harsh manual labor for sellers now only take less than 24 hours. So definitely that's a real game changer. But when we started rolling out this new feature, we've discovered that we have the potential to extract even more data out of seller catalog from a source that is, for now, completely unexploited, which are product images. So we've seen that with product images, we can get a lot of data that is not included in the seller catalogs. And we've devised a semantic schema allowing us to extract this data thanks to GenAI today. Our data scientists have created this, as you can see here, we've got some structured data with more description about the type of product images that the sellers have in their catalog. So we've got information such as background, lighting, scene type, perspective, that can be quite important to help us standardize seller images according to marketplace wishes. And this structured data, once extracted, can fuel a lot of downstream GenAI use cases, such as image ordering, background generation, and image standardization. But technically speaking, how do we make this work at scale? This is why today I'm introducing a blueprint for a cloud-native inference stack to extract structured data from images. Let's start with the building blocks. On the left-hand side, we've got the inputs. So, of course, seller catalog, picture an Excel sheet with a list of products, one product per row, a lot of attributes such as description, metadata, media URLs, but also the list of operator requirements, how the data should look on their marketplaces. The first part with the text go through catalog transformations, which are LLM power transformations that we've seen just before with enrichment, translation, etc. These are made effective thanks to Spark pre-processing. So we leverage batch ingest, we leverage distributed transforms. So that part already works, it's already in production, it works well. Now onto the images. We've introduced two building blocks. We've got the vision language model at first. So this model will serve to extract the structured data that we've seen from product images. We definitely align it with textual description that we find in the product descriptions. And then what happens is that the vision language model, we've opted to host it on our own infrastructure. We leverage for that K-Serve, which is a framework for a cloud-native inference. It allows us to provide stable endpoints and safe rollouts. We've been using VLLM, which is the framework that's quite widely used today to serve LLM endpoints with OpenAI standard REST API, and Kserve supports it natively, so that works great. Once we extract the structured data from the from the images, then we can send this data to downstream GenAI services using the use cases we've seen before, image ordering, etc. This can be any number of AI provider. For us, it could be a third party with OpenAI, for example, but it could also be AI infra providers such as Anyscale, so we host our models there, or we can host it on our own infra since we already have Kserve deployed. So any number of these can work, a combination of these can work as well, as long as we get the desired output. With the text and the images, now standardized to the operator's wishes, we've got the transformed catalog that is ready to go on live and help the seller achieve their sales target. So now we've got this in place, but the first thing we can think about is, okay, these are the building blocks. What are the optimizations we could think of? So everybody in this room knows that GPUs are hard to come by. And when they do come by, they come by at a cost. So how do we reduce that cost? How do we make sure that we're not reprocessing the same image twice? But also, are there any optimization techniques that we can leverage to use even smaller GPUs and make sure that we've got a bigger fleet or reduce our budget? Any justification could be good. To this end, we've introduced two optimizations, starting with caching. So adding a cache layer allows us to cache model results. Simple, right? But effective. We use the image hash and the service version in order to retrieve the model results. And every cache hit allows us to save 30 seconds per product on average, which is not negligible. So it means that we are avoiding GPU and we are replying faster to the end user. Our caching backend today is Amazon DynamoDB, but it could be any other caching technology. And another optimization, the second one, is the addition of a LoRA. So a LoRA is a low rank adaptation. It's a layer added on top of a base model that is carefully fine-tuned on domain knowledge by our data scientists. This allows us to improve accuracy. We couple that with quantization, which means that we're reducing the numerical precision of the model in order to make the compute faster and to decrease the memory footprint on the GPU. Once we've put that into production, we got two further questions. So as I've described, we can call any number of AI providers. It could be our own. It could be something hosted on Anyscale. It could be OpenAI. So how we keep tabs? How do we keep track of AI providers and quotas? But also, we've seen bursts up to 80K products per catalog, even higher sometimes. And the GPUs, making them scale as fast as the incoming catalogs and the incoming volume of data is a bit hard to maintain. So how do we regulate traffic? How do we anticipate the demand? And how do we make sure that we have a good customer experience at the end? This is why we're currently working on two further optimizations. The first one is adding queuing. Queuing allows us to parallelize, to decouple responses from requests from responses. It allows us to buffer bursts and anticipate GPU demand, especially if we check the number of incoming products within the queue, then we can anticipate a bit earlier to increase our fleet. Regarding the multiplicity of AI providers, we've chosen to wrap all our requests with an AI gateway. This allows us to centralize authentication, keep tabs on quotas, and improve governance. AI gateways often come with the unified observability, but also a multi-provider abstraction, which means in case of failover, in case of A/B testing, we can switch from one provider to the next painlessly. That's the full blueprint. But of course, no blueprint is complete without an honest discussion on trade-offs and key considerations. I guess all of you have questions about what I've just presented, but let me anticipate that with 3 key considerations. The first one is latency. So definitely every time I'm adding a new layer to our blueprint, I'm adding a bit of latency. So queuing introduces a wait time by design, because we're making the request just wait. Also the fact that GPU cold starts are noticeably long with big models. So auto-scaling can take several minutes, and this can add to the latency. Plus, our tests have shown that AI gateways may add overhead to each request that's incoming. So 2 questions to ask here. What are the SLAs for our use case? Are there any trade-offs that we can make? Can we differentiate between different use cases and allow for latency in some and reduce latency in others? This can help us find the best solution for our use case, and definitely there's no one response to every problem. So what's important is to be able to have eyes on what's happening by monitoring indicators to ensure that we've got acceptable SLOs depending on our use case. We can differentiate processing patterns between use cases. So batch is different than real-time, but also big catalogs or big data sets are different than small catalogs. We can definitely deploy smaller models for latency-sensitive use cases and deploy larger models for use cases that need more accuracy, for example. A new feature that we started experimenting with is implementing model weight streaming to reduce GPU cold start. This is something that's currently available with NVIDIA's Run AI. It's available on GCS natively, and this is something that allows us to parallelize the transfer of model weights onto the GPU memory, therefore reducing autoscale time. And finally, definitely optimize AI gateways configuration with caching and distribution. So that's for the first consideration, latency. The second one is operational overhead. I guess when I spoke about having a lot of different AI providers, most of you had this question in mind. Okay, a lot of AI providers, a lot of choice, but that means a lot of work. So adding this diversification increases complexity because it means that there are people behind it working on operations, working on integration, monitoring, and making sure that the vendor relationship is strong. But also, something to consider is the fact that AI libraries move super fast. I guess you've all updated several minor versions in a month. So what we've already seen, for example, with VLLM on Kserve, is that the latest minor versions with the most interesting new features are not yet supported, be it on open source software or even on managed inference. So here we can ask ourselves 2 questions. Do we have the team necessary to put that in place? And also, can we wait, let's say, 3 or 4 months until this new up-and-coming feature is available by a managed inference service? This also could be a valid question. So definitely to be able to address this provider complexity, we can unify observability with standardized metrics across all providers, like be it the observability feature that we can leverage in the AI gateway, or use Datadog or Prometheus with Grafana. Anything can be leveraged to make sure that we've got a good way to compare different providers. Definitely use infrastructure as code because it helps operations. A good tip is to use OpenAI compatible APIs, which means we can switch from one provider to the next as painlessly as possible. And also regularly reassess build versus buy decisions as offerings mature because it evolves very fast. And finally, the last consideration is results quality. Definitely, once we use quantization, it means we're reducing the numerical precision of the model, therefore reducing accuracy. Also, the fact that we're choosing smaller and faster models over bigger but more accurate ones, it can depend on the use case. This could be a valid or invalid decision depending on the use case we've got at hand. Also, by using smaller models, we have to keep in mind that we're using smaller context windows. So for prompt engineering, this could be a bit complex sometimes to grab the entire context of what's happening. So, of course, it's going to be the same questions that we're going to ask ourselves. Can we differentiate between the use cases and use adaptive model selections between, let's say, a big catalog or a big data set versus a smaller one? Definitely leverage LoRA. This is something that's worked quite well for us because it allowed us to have domain-specific fine-tuning, which can recover the quality lost to quantization. And finally, have an evaluation pipeline. This is something that's a must. A lot of people are talking about this. There's no a solution that's going to allow us to have the best evaluation possible, be it for VLMs or LLMs, but at least we can have a human-in-the-loop verification. It could be LLM as a judge as well. We can combine all of these techniques to make sure that we've got eyes and we're seeing if there's a drift. And that's it for how to go from product images to structured data with vision language models at marketplace scale, in production, and within budget. So of course, GPU budgets don't need to scale with image volume. We can leverage parallelization, optimization, and smart infrastructure choices to be able to achieve this high level of inference. A quick reminder about the optimization. So we can add a caching layer. We can use LoRA fine-tuning plus quantization. We can use event-driven queuing as well as an AI gateway to monitor everything that's going on. And as to the key considerations that I've evoked at the end, keep an eye on end-to-end latency, operation overhead, and results quality. That's it for me. Thank you all for listening. I hope you've enjoyed it.